We've spoken about the temperature of the Earth, but how do we actually calculate the temperature theoretically? Now, if we consider that the temperature is actually constant, let's ignore global warming for the moment, then if a temperature of the Earth is constant, the incoming radiation, the shortwave radiation from the sun, has to equal the outgoing radiation from the Earth, the cooling of the Earth. This is true for any object even. If an object is warming, it's getting more energy than it's losing. And if it's cooling, it's losing more energy. There's more output than input. If the temperature is constant, there has to be a balance between the two. The incoming energy has to be equal to the outgoing energy, which will give us a constant temperature. So for the Earth, schematically, we can say the input of the energy is what we're getting from the sun, the solar constant, 1,362 watts for every square meter. The outgoing is the emission of radiation from everywhere. But let's first talk about the left-hand side of this equation. What we see is that the sunlight is actually only lighting up one side of the planet, the side that's in the daytime. In the nighttime, it's dark. We don't get any radiation during the nighttime. Again, we define the amount that we get for every square meter perpendicular to the sun rays outside the atmosphere as the solar constant, 1,362 watts per square meter. That's the average radiation we get throughout the year at the Earth's distance of 150 million kilometers from the sun. But as I just mentioned, the solar radiation is only really illuminating one side of the planet, wherever we have daylight, which is only half the planet. And from the sun's perspective, the sun simply sees a disk in the sky, which has a radius of the Earth's radius, RE here. And so what's actually being heated by the sun, we can think of this as an area of a disk, which is simply pi r squared. We can see over here, the area of a disk. But the Earth is rotating around its axis, and so this energy, which we only get on one side, has to eventually warm the whole sphere, the whole planet. And the area of the Earth is 4 pi r squared. The difference is simply a factor of 4. Area of a disk is pi r squared. The area of a sphere is 4 pi r squared, where r is the radius of the Earth. So eventually, if we average over time, the amount of radiation coming into the system is the solar constant, which is how much we get at the distance of the Earth, S0, times the area that it actually shines on, divided by the area of the sphere. And so basically, we have this, because the pi r squared basically cancel out, we're left just with the solar constant divided by 4, 1,362 divided by 4, which gives us 340 watts per square meter on average everywhere around the planet. Obviously, this is not true because in the equator we get more than we get at the poles. Again, daytime we have sunlight, nighttime we don't. But if we want to look at the average for the whole planet, every square meter on the planet, how much energy we get from the sun coming in, it's 340 watts per square meter on average. Now that would be the case if all of that energy made it down to the surface. And now we have to introduce an expression or a term we call albedo. Some of this radiation coming in gets reflected back to space and depends on what the sunlight is actually going to hit, if it's going to be a white cloud or the dark oceans or the ice sheets or a rainforest. And so we can define the albedo of different surfaces on the Earth and also things in the atmosphere. And this basically is the reflectivity of the surface or the clouds or some absorber in the atmosphere. And we measure albedo in percentage. So it can be either from 0, where everything gets absorbed, to 100% albedo, where everything gets reflected. And here you can see in the example, something which is dark has a low albedo, like the oceans or forests, which are dark in color. They'll absorb a lot of the solar radiation, reflect a little bit, but most of it will be absorbed. And we can go to something which is a high albedo, like the ice sheets or even deserts or clouds, which will reflect most of the sunlight, absorb a little bit. And so we have a different amount of absorption of the sunlight depending on what the albedo is of the object or the surface of the Earth at any latitude, any longitude. And if we change the albedo, we can change the temperature of the Earth. So as the albedo increases, which means we have more reflection, more reflectivity. There'll be a decrease in the amount which is absorbed. The temperature of the Earth, or the temperature of the location, will decrease. So we'll see later on, using different examples which actually occur in nature, if we change the albedo, we can actually change the temperature or the amount of energy coming into the system. So here we can see some examples of albedo. Snow, for example, is bright and white clouds, so they reflect between 70 to maybe 95% of the radiation which actually hits them. So if the sunlight coming in on the bright snow, most of it will be reflected back out to space. On the other hand, the oceans will reflect maybe 10 to 40% depending on the angle of the sun, depending on the time of the day, of the latitude. Forests are very dark. They absorb maybe most of the radiation, reflecting maybe only 3 to 5%. And when we average everything over the whole planet, we get a value of around about 30%. 30% of the energy coming in from the sun is immediately reflected back to space. And so we can only actually use 70% of that. If the albedo is 30%, then the amount absorbed in the system is 1 minus big A. Big A is the albedo, which is 70%. So when we get the radiation from the sun, only 70% of that can we actually use. So now we have to add in the equation at the bottom, we have the solar constant divided by 4 because of the ratio of the areas. And then we have how much is absorbed, which is 1 minus the albedo, which is 70%. So we have 340 times 0.7, which now leaves us with 238 watts per square meter. So because of the color of the Earth, the clouds, the ice sheets, the oceans, we actually only have 70% of that energy coming in to use to drive the weather, to affect the climate, and to warm the planet. Now let's talk about what's leaving on the right-hand side of that first equation of the cooling of the planet, the outgoing radiation. So the outgoing radiation actually occurs everywhere, not unlike the incoming, which is only on the daytime side. The outgoing occurs everywhere, from the South Pole to the North Pole. Anywhere where the temperature is above 0 degrees Kelvin, we'll have some radiation being emitted from that location. And there's no place on Earth which is at 0 degrees Kelvin. In fact, no place even in the solar system, even in the furthest depths of outer space, the coldest temperatures are around about 4 degrees Kelvin. In fact, you can never really get to 0 Kelvin because you need something colder to cool things down to 0 Kelvin. And so definitely on the Earth, there's nothing that cold. And so from every place, even from the ice sheets, from clouds, anywhere on the planet, we have radiation. Therefore, you see these arrows are going out in all directions, not only on the daytime side of the planet. So the radiation, we already spoke about this previously, leaving any object is defined by the Stefan-Boltzmann law that we spoke about before. The energy leaving is simply a function of the temperature to the 4th power times this little a, which is the Stefan-Boltzmann constant. So the little a doesn't change at all. That's constant for all of the calculations. The only thing that changes around the planet is the temperature of the surface, the temperature of the clouds, and that temperature will define how much radiation is leaving the planet, what we call the terrestrial or the long-wave radiation, all of it which is occurring in the infrared part of the spectrum. So again, at equilibrium, if the temperature is not changing, constant temperature, the input has to equal the output. So we have here again our simple equation. On the left-hand side of the equation, we have the input, the solar constant, S0 divided by 4, times how much gets absorbed, 1 minus the albedo, 70%. And this equals the output, the little a, which is a constant, times the temperature of the planet to the 4th power. So we can put these numbers now into the equations. We know what the solar constant is. We said A is 0.3 or 30%. We know what little a is, and then we can try to solve this equation. And what comes out of this equation is that the temperature of the Earth is 255 degrees Kelvin, which is minus 18 degrees Celsius. Well, that's not what we've spoken about before. We said the temperature of the Earth is 15 degrees. So something's missing in this calculation. And what's missing is the atmosphere, or the greenhouse gases in the atmosphere. What we've calculated here is the temperature of the Earth without an atmosphere. If we didn't have an atmosphere, and we didn't have greenhouse gases in the atmosphere naturally, the temperature of the planet on average would be minus 18 degrees. And the oceans would be a solid block of ice. And again, we wouldn't have any life on planet Earth. And so what we left out of this simple model is the effect of the greenhouse gases in the atmosphere. And the greenhouse gases, we will speak about them more in the course, but basically the main natural greenhouse gas is water vapor. Water vapor from evaporation from the oceans, from vegetation. Water vapor can trap the infrared radiation, and it acts like a blanket on the planet to warm up the temperatures. But we have other greenhouse gases, methane, carbon dioxide, nitrous oxide, and these molecules by definition trap in the infrared radiation and warm up the climate. How much do they actually trap it in? We'll talk in a second, but the role of the greenhouse gases is to reduce the amount of radiation leaving the planet. So here you can see in this little animation some heat or infrared radiation which is being absorbed by this carbon dioxide molecule. What we see is that the radiation which is absorbed causes the molecule to rotate or to wiggle, losing some of that energy, and what's released on the other side of the molecule is less energy. So overall, we're keeping some of that energy in the system to warm up the atmosphere. You can see in another kind of animation here that the heat in the red arrows or the pink arrows being emitted from the surface of the Earth after they've been heated by the solar radiation in yellow, if these impinge or they interact with greenhouse gases in the atmosphere, and on the right you can see for this carbon dioxide molecule, they can react in different ways depending on the energy of the radiation. You can see that the middle atom can move up and down or can move sideways, it can rotate. All of these are different types of energy levels, but the bottom line is that less energy will actually leave the Earth's atmosphere, less will go out to space, more will remain inside, heating up the planet. So we call this the transmissivity, how much energy from the surface gets transmitted through the atmosphere and makes it all the way to space. And today we know that only 62% of this, 0.62, make it all the way through. We use the symbol, this little Greek letter T or tau, which represents how much gets transmitted through the atmosphere. So on the planet Earth, on average, from the 100% which leaves the surface of the Earth, the heat leaving the surface, 62% make it out into space. And 1 minus tau represents the absorptivity, how much gets absorbed in the atmosphere. 1 minus 62% is 38%. And so 38% of the radiation leaving the surface of the Earth gets trapped and absorbed in the atmosphere by the greenhouse gases, mainly by water vapor, but also by the other greenhouse gases, and warms up the climate significantly. And if we put now that transmissivity parameter into the equation of what's leaving the Earth, so before we had that the output of radiation, R out, was 1 times a t to the 4th power. Now instead of it being 100% leaving, we only have 62% leaving. And if we we solve the equation with the 0.62 on the right-hand side of the equation, now we get to approximately 14 degrees, 15 degrees of the surface temperature on average around the planet. What this says is basically that because we have an atmosphere and we have a natural greenhouse effect, the planet warms by 32, 33 degrees, from minus 18 degrees up to plus 14 degrees, all because of the greenhouse gases in the atmosphere, and primarily on a natural basis due to water vapor which evaporates from the ocean and from plants. Without that water vapor in the atmosphere, we would be minus 18 degrees on average, and we wouldn't be sitting here talking today. So to summarize, we have a natural greenhouse effect on the Earth. On the top, we can see what would happen if we didn't have this greenhouse effect, if we didn't have the atmosphere. The solar radiation coming into the planet would be heating the surface as it does normally, but the energy released, all of it would go out to space, and on average, we would have a temperature of the globe, of the Earth, of minus 18 degrees. Because we have greenhouse gases in the atmosphere, mainly water vapor on a natural basis, this traps in a lot of this heat. 38% remains in the system, and we warm up the planet Earth to plus 14, plus 15 degrees, and allows us to have liquid water on the planet and allowed life to evolve on planet Earth.